Just 6 minutes ago, high in the mountains of Chile, a machine the size of a small truck snapped yet another photograph of the night sky. That one exposure joined a pile of evidence so bizarre that researchers are still trying to make sense of it. Because what this instrument has uncovered in under a year isn't a single discovery. It's an avalanche of them. A ribbon of stars stretching twice as wide as our own galaxy. A space rock spinning at a rate that shouldn't be physically possible. A star that might have vanished into a black hole without so much as a flash. And a wanderer from beyond our solar system that slipped past Earth completely undetected, until someone finally checked the archives. This is the story of the Vera Rubin Observatory. And if this is the first you're hearing of it, you're about to find out why so many astronomers are calling it the single most disruptive instrument ever aimed at the heavens. Let's rewind to the exact moment everything shifted. On June 30th, 2026, after a quarter century of building, testing, setbacks, and mounting anticipation, the Vera Rubin Observatory finally flipped the switch on its real mission. Not a dry run, not a preview. The genuine 10-year clock started ticking. The project is officially called the Legacy Survey of Space and Time, and here's what that means in everyday terms. Roughly every 3 to 4 nights, the observatory captures the entire visible southern sky. Not a handful of galaxies, not one region, all of it. Then it lines that fresh image up against the previous one. The instant anything shifts, a point of light moving, growing brighter, fading, showing up, or disappearing, the system catches it immediately. Researchers at the SLAK National Accelerator Laboratory have confirmed that once the survey hit full stride, it started producing close to 7 million alerts every single night. 7 million. Every night, without fail. That's not a photo album. That's essentially a nervous system wired straight into the cosmos. To grasp how enormous a jump this represents, rewind 12 months to June 23rd, 2025. The day humanity got its first real glimpse of what this telescope could accomplish. Using barely 10 hours of test observations, gathered over just 7 nights, the Rubin team unveiled a single stitched-together image of the Virgo cluster. Packed inside that one frame were roughly 10 million galaxies. Not stars, entire galaxies, each one potentially home to billions of stars and uncountable hidden worlds. And according to the NSF and Noir Lab, that staggering figure represented only about 1/20th of 1% of everything Rubin is projected to catalog across its full decade-long survey. If 10 million galaxies already feels impossible to wrap your head around, consider this. Rubin's ultimate goal is to observe somewhere near 20 billion galaxies. We've barely cracked the door open, and the room behind it is already too vast to see the far wall. But raw numbers alone don't explain why so many scientists are simultaneously rattled and electrified. It's what was buried inside that very first batch of data that shifted the mood in observatories worldwide. Hidden in the earliest images, astronomers noticed something that had never been logged before. A stream of stars stretching an estimated 163,000 light-years, torn loose from the spiral galaxy Messier 61. That's longer than the entire diameter of our own Milky Way. A structure of that magnitude, sitting there quietly in plain sight, and no telescope before Rubin had the field of view, the depth, or the patience to spot it. That's not a minor footnote. That's proof that massive, galaxy-altering events have been unfolding around us all along, and we simply lacked the right instrument to catch them in the act. Here's the part worth sitting with for a moment. Every telescope that came before this one worked like a photographer. Aim, focus, shoot, done. One target, one exposure, one frozen instant preserved forever. Hubble delivered breathtaking detail. James Webb opened up the ancient infrared universe. But neither was designed to circle back to the same patch of sky over and over, comparing what's there now against what was there before. Rubin was built from the ground, up around that exact concept. Scientists have taken to describing it in a very particular way. Rubin doesn't just take pictures of the universe, it gives the sky a memory. And a universe with memory behaves completely differently from one trapped in a single photograph. It starts giving up its secrets. A star that's suddenly missing becomes a clue. A dot that shifts position becomes an asteroid. A faint smear of light becomes a 163,000 light-year river of stolen stars. So if just 10 hours of preliminary data already produced 10 million galaxies, a hidden galactic river, and enough new asteroids to make headlines, the obvious question becomes, what happens once this machine is running at full capacity for an entire year? What does year 5 look like? What about year 10? But before we get there, you need to understand exactly how strange some of these early finds already are, because one particular asteroid is currently defying physics as we understood it. Stick around, because next we're diving into an object called 2025. MN45, a rock roughly twice the height of the Empire State Building, spinning so violently it should be flying apart in real time. And nobody can fully explain why it isn't. Let's talk about the asteroid that has no business behaving the way it does. Its designation is 2025 MN45. On paper, it sounds unremarkable, just another rock drifting through the asteroid belt between Mars and Jupiter. But the moment astronomers studied its behavior closely, it turned into one of the strangest objects cataloged in recent memory. A peer-reviewed study published in the Astrophysical Journal, Letters, on January 7, 2026, measured this asteroid at roughly 710 meters across, nearly double the height of the Through the Dark. And here's the detail that made researchers stop and double-check their instruments. This asteroid completes one full rotation every 1.88 minutes. Under 2 minutes for something the size of a skyscraper to spin all the way around. To understand why that's so alarming, you need to know what most asteroids this size are typically made of. A team led by astronomer Sarah Greenstreet of NOIR Lab and the University of Washington explained that most rocks in this size class are what scientists call rubble piles, loose clusters of stone and dust barely held together by weak gravity, like a heap of gravel that's just barely clinging to itself in space. A rubble pile spinning that fast shouldn't hold together at all. Centrifugal force should tear it apart, flinging debris across the solar system. Yet 2025 MN45 remains fully intact, still spinning at a rate scientists openly admit they never expected to find in an object this large. Co-author Dmitry Vavilov of the University of Washington put it bluntly: for asteroids around 700 meters wide, nobody anticipated finding one spinning faster than every 10 minutes, let alone one nearly 5 times faster than that. So what's holding it together? The leading theory is nearly as wild as the discovery itself. Greenstreet's team believes 2025 MN45 might be a shard blasted off the dense, superheated core of a much larger planetary body that once existed early in our solar system's history, a body later obliterated in a violent ancient collision. If that theory is correct, this isn't just a rock. It's a surviving fragment of a planet that no longer exists, spinning silently through space for roughly 4.5 billion years. And we only just noticed it in 2025. And MN45 wasn't alone. That same research effort identified 19 newly confirmed fast rotators in total, every one of them larger than a football field. 16 were classified as superfast, completing a rotation somewhere between 13 minutes and 2.2 hours. 3 were classified as ultra-fast, spinning in under 5 minutes, with 2025 MN45 sitting at the extreme edge of that group, alongside 2 others, 2025 MJ31 and 2025 MK41. What makes this even more remarkable is the timeline. This entire dataset came from just 7 nights of observation gathered back in April and May of 2025 during Rubin's very early commissioning phase, months before the telescope had even begun its real 10-year mission. This was a warm-up, a stress test, and it already shattered a record that had gone unchallenged for the entire history of asteroid science. Zoom out further, and the scale becomes almost impossible to process. During Rubin's pre-survey calibration window in early 2026, a stretch of roughly 6 weeks, the observatory identified more than 11,000 previously unknown asteroids, including 33 near-Earth objects and 380 objects orbiting far beyond Neptune. 11,000 new asteroids in 6 weeks before the actual survey had even officially begun. Now, here's the number that should genuinely stop you in your tracks. Scientists at Rubin Observatory and NOIR Lab project that in its first full year of operation, the telescope could discover around 1 million previously unknown asteroids. 1 million. For context, that's roughly equal to every asteroid humanity has painstakingly cataloged over the past 200 years, combined. 2 centuries of work potentially doubled in 12 months. Why should any of this matter if you're not an astronomer? Because asteroids aren't just floating debris, they're historical records. Each one holds physical evidence of how our solar system formed, how planets collided, drifted, and eventually settled into the orbits we know today. Greenstreet herself pointed out that identifying asteroids locked into specific motion patterns, particularly ones synchronized with Neptune's orbit, could, finally, help researchers trace how the outer planets migrated to their current positions billions of years ago. And there's a more immediate, practical reason to care too. Scientists are hopeful Rubin will dramatically improve our ability to spot small, meters-wide asteroids just before they enter Earth's atmosphere, what researchers call imminent impactors. Current simulations suggest Rubin could catch roughly one of these events per year, and instead of just a few hours of warning, it could give scientists a couple of days of advance notice before a fireball lights up the sky. That's enough time to point instruments at exactly the right patch of sky, deploy sensors, and actually watch the moment of impact unfold live, rather than reconstructing it after the fact. So we now have a telescope that's uncovered a rogue fragment of an ancient, shattered planet, spinning nearly 5 times faster than physics comfortably allows, sitting inside a haul of 11,000 newly discovered asteroids found before its real mission had even started. If this is what a warm-up phase produces, what happens when this same machine turns its attention towards something even stranger? Something that doesn't spin or orbit, something that simply vanishes. Up next, the discovery some astronomers are calling the most unsettling of all, a star in the Andromeda Galaxy that may have died without ever exploding, and a silent visitor from another solar system that slipped past Earth for 10 days before anyone noticed. Now we arrive at the part of this story that genuinely rattled astronomers, because this isn't about something appearing in the sky. This is about something disappearing from it. Scientists call it a failed supernova, and it might be one of the strangest forms of stellar death physics allows. Normally, when a massive star reaches the end of its life, it goes out in the most violent way imaginable, exploding outward with enough force to briefly outshine an entire galaxy. That's a supernova, bright, dramatic, impossible to miss. But a failed supernova does the exact opposite. Instead of exploding, the star simply caves in on itself and collapses directly into a black hole. No blast, no flash, no warning. One moment, there's a massive star. The next, there's nothing where it used to be. For decades, this remained purely theoretical because catching a failed supernova in the act is uniquely difficult. You're not searching for something bright. You're searching for an absence, a star that used to be there and suddenly isn't, in a universe crowded with billions of stars that all look roughly alike until one of them quietly ceases to exist. According to research published in the journal Science in February 2026, astronomers identified a possible candidate for exactly this kind of event in the Andromeda Galaxy, roughly 2.5 million light-years from Earth. Stephen Smart of the University of Oxford, who leads the science team behind one of Rubin's key data alert systems called LASER, explained that Rubin is uniquely positioned to catch more of these events because its images reach roughly 100 times fainter than other sky surveys. In plain terms, Rubin can detect the kind of quiet stellar death that every previous survey on Earth was simply too weak to notice. If that Andromeda candidate gets confirmed, it becomes direct evidence that some of the universe's most massive stars are collapsing into black holes silently with zero announcement, which means there could be far more black holes scattered across the cosmos than anyone has ever accounted for. This is exactly the kind of discovery Rubin's alert system was built to catch, and the scale of that system is almost hard to put into words. On February 24th, 2026, Rubin ran a live test of its alert pipeline, photographing a patch of sky with a strong historical baseline already established. In a single night, it generated 800,000 alerts. Every object that changed, appeared, or vanished got automatically flagged and logged. Smarty. Described it simply, everything that changed triggered an alert, and that was still just a test. Once the full legacy survey of space and time launched on June 30th, 2026, the system ramped up to its real operating scale, an estimated 7 million alerts and roughly 20 terabytes of new data every single night. 7 separate data broker networks around the world, including LASER, now exist purely to help astronomers sort through that fire hose in real time. One of the biggest reasons any of this matters comes down to something called a Type Ia supernova, a very specific kind of exploding star astronomers use as a cosmic measuring stick. Back in the late 1990s, 2 research teams studied fewer than 100 of these supernovae and made one of the most important discoveries in modern physics, that the expansion of the universe is accelerating, driven by a still mysterious force we now call dark energy. Once Rubin's full survey reaches capacity, scientists expect to find around 250,000 Type Ia supernovae every single year. Not 100, 250,000 annually. Researchers are hoping this flood of new data can finally help resolve the Hubble tension, a long-standing disagreement in physics, where the modern universe appears to be expanding faster than early universe measurements predict it should. If Rubin's supernova data can settle that argument, it would resolve one of the biggest open questions in all of cosmology. But stars aren't the only things slipping through the darkness that Rubin is built to catch. It's also becoming one of the most powerful tools ever constructed for tracking visitors from beyond our solar system entirely. Across all of recorded history, astronomers have confirmed only a small handful of interstellar objects, asteroids or comets, that formed around other stars and simply passed through our neighborhood before continuing on their way. One of the most recent was an interstellar comet named 3I Atlas, first announced on July 1st, 2025, after being spotted by a separate telescope network called ATLAS. Here's the part that genuinely stunned researchers. When astronomers went back and combed through Rubin's own archived data afterward, they discovered Rubin had already captured images of 3I Atlas a full 10 days before Atlas ever announced its existence. 10 days. The object had been sitting quietly inside Rubin's data the entire time. Nobody had simply gone looking yet. Astrophysicist Rosemary Dorsey of the University of Helsinki said scientists genuinely don't know how many more interstellar visitors Rubin might catch once the full survey is underway, estimating it could be anywhere from 5 to 500, depending on how frequently these objects get flung out of other star systems in the first place. So sit with what that actually means. A telescope that can retroactively spot a visitor from another star system 10 days after it already passed by completely unnoticed in real time. A star in a neighboring galaxy that may have died in total silence. An alert system processing 7 million changes to the sky every single night. More information than human astronomers could ever fully process on their own. This isn't a telescope anymore. This is a live surveillance system for the entire visible universe. And yet, everything we've covered so far, the asteroids, the vanishing stars, the interstellar visitors, is still just the surface layer. Underneath all of it lies the actual reason Rubin was built in the first place, and it has nothing to do with what we can see. Coming up, the invisible universe itself, the dark matter and dark energy that make up the overwhelming majority of everything that exists, and why scientists believe this observatory might finally answer questions humanity has been chasing for over 90 years. Everything we've discussed so far, the galaxies, the asteroids, the vanishing stars, the visitors from other solar systems, is all part of the universe we can actually see. But here's the number that should make you sit back for a second. Everything visible in the cosmos, every star, every planet, every galaxy, every human being who has ever existed, makes up only a small slice of what's actually out there. The rest is made of dark matter and dark energy, two forces that dominate the universe and that scientists still can't directly explain. And this is where the story of this observatory turns personal, because it was built specifically to hunt for them, and it was named after the woman who first proved they were real. The observatory carries the name of Vera Rubin, an American astronomer whose work in the 1970s permanently reshaped physics. Rubin studied the rotational speed of galaxies and noticed something that simply didn't add up. Galaxies were spinning so fast that, based purely on their visible matter, they should have been flying apart entirely. Something invisible had to be holding them together, supplying gravity that no telescope could detect. That invisible substance is what we now call dark matter, and Rubin's observations became some of the strongest evidence proving it exists. She never lived to see this telescope carry her name into operation. But in a very real sense, this entire 10-year mission is a continuation of the question she first asked half a century ago. What is actually holding the universe together? Here's how the observatory intends to answer that. As light travels across the expanding universe toward Earth, it stretches and shifts toward the red end of the spectrum, a phenomenon known as redshift. The more stretched the light, the farther away its source. By measuring this shift across billions of galaxies, a technique called photometric redshift, Rubin can map how mass, including invisible mass, is distributed across unimaginable distances. Astronomer Kristen Dage of Curtin University confirmed that Rubin's early preview data already showed this technique performing at least as well as other leading telescopes. And once the full 10-year survey wraps up, Rubin is expected to measure the redshift of roughly 4 billion galaxies out of the 20 billion it will ultimately observe. 4 billion galaxies mapped for distance and structure, effectively building a chart of where the invisible skeleton of the universe actually sits. And dark matter is only half the invisible puzzle. The other half is dark energy, the mysterious force that appears to be causing the universe's expansion to accelerate rather than slow down. Scientists still don't know what dark energy actually is, where it comes from, or whether it will continue indefinitely. But by tracking roughly 250,000 Type Ia supernovae every year once the survey reaches full speed, Rubin is expected to give researchers one of the most detailed independent tests ever conducted of whether dark energy behaves as a fixed constant, or whether it's been changing throughout the history of the universe. If it turns out dark energy is evolving rather than constant, that would rank among the most significant findings in the history of physics, forcing scientists to rewrite fundamental assumptions about how the universe will ultimately end. So, step back and take in the full picture one more time. In June 2025, this telescope opened its eye for the very first time and immediately produced 10 million galaxies in a single image, along with a hidden 163,000 light-year river of stars nobody had ever cataloged before. Within months, it had identified more than 11,000 new asteroids, including one spinning almost 5 times faster than physics comfortably allows. By February 2026, it had flagged a candidate star in Andromeda that may have collapsed into a black hole without ever exploding, and confirmed it had silently photographed an interstellar visitor from another solar system 10 days before any other telescope on Earth even noticed it was there. And on June 30th, 2026, it switched on its true 10-year mission and began generating 7 million alerts about the changing sky every single night for the next decade. We spent thousands of years staring up at a sky that seemed permanent. Fixed stars, frozen constellations, a universe so vast and so slow that a single human lifetime felt too short to ever catch it moving. The Vera Rubin Observatory has already proven that was never true. The sky was never still. We simply never had a machine capable of remembering what it looked like yesterday, so it could catch exactly what changed today. Now we do. And it's already uncovering failed stellar deaths, rogue asteroid fragments, hidden galactic rivers, and visitors from other stars, in less than a year of partial operation. So here's the real question, and I want you to genuinely sit with it before you go. This telescope has 10 years left to run. It has barely scratched the surface of what it's capable of finding. If the first few months alone produced discoveries this strange, what's waiting in year 5? What's waiting in year 10? How many hidden black holes have already formed in complete silence that we've never detected? How many interstellar visitors have already drifted through our solar system without a single human being noticing? We're not just watching a telescope collect data anymore. We're watching the universe get caught, in real time, in the act of changing. If stories like this pull you in, the way the universe keeps quietly rewriting everything we thought we understood, make sure you're subscribed, because this observatory is going to keep making headlines for the next 10 years, and you don't want to miss what it finds next. Drop a comment below and tell me which discovery from this video shocked you the most. The spinning asteroid, the silent dying star in Andromeda, or the interstellar visitor that slipped past us for 10 days completely unnoticed. And if you want to go even deeper into how astronomers are racing to map the invisible universe, there's another video linked right now that you need to watch.